In this video, I'm going to show you how to solve a linear regression problem directly using the normal equation in Python. The first thing that we want to do is import the libraries that we're going to be using. And we're going to be using NumPy and also matplotlib because we want to create a few plots. So say import NumPy as np and then import matplotlib.pyplot as plt. So now what I want to do is generate some random data for x and y. So I'm going to say that x, and I'm just going to use the random function in NumPy to generate some data. So np.random.rand 50. And so what this is doing is it's generating 50 random values between 0 and 1. And I actually want these values to be, and I'll just show you this. So basically I have an array now that has 50 values and they're between 0 and 1. And I want to make these values a little bit larger, so I'm going to multiply this by 3. So then you can see now the values are ranging between 0 to 3. And then we need to generate some data for y, and we want to generate linear looking data. So one of the assumptions with the linear regression model is that your data is linear. The way I'm going to generate linear looking data is I'm just going to use the equation for a line. So I'm going to use 2 plus 3x. So x is the array that we just generated. And then what I'm going to do to make this a little more, to make this look a little more like real data is I'm going to add some random noise to it. So I'm going to say plus np.random.rand 50, and then we can look at what y looks like. Whoops. So these are the values that we have for y. And instead of just looking at these, it makes more sense to plot them because then we can kind of see what this data actually looks like. And this is if you were importing, so I'm generating this data, but if you were importing some data, you would want to plot it to see what it looks like before you apply a model to it to make sure that you're applying a model that makes sense. So like in this case, since we're using linear regression, we want to make sure that our data is linear. I'm going to plot this, so plt.plot, and then this is x, y, and then I want to plot points, not a line. So I'm going to put a 0 or an O, and then plt dot, and then I'm going to put some labels just so it's clear what's on the different axes. So plt dot y label y. Alright, so this is the data that we just generated. What I want to do before jumping into actually solving this model is I want to show you the equations real quick that we're using, just as a reminder. So first of all, we're solving, well, so our model is y equals x beta. And remember, y is a column, is a vector. So we have y1 to yn, and this is what we generated. And remember, we have 50 values, so I can actually change this. This goes to 50. And then this is equal to, with the x matrix, this is actually 1. So our first column is always 1s. And then since this is a simple linear regression model, we only have independent variables. So this is x1, and then this goes down to x50, and then this is multiplied by beta naught and beta 1. What we're actually solving for is beta naught and beta 1. The way that we're solving that is we're using the normal equation, and so beta is equal to x transpose x inverse x transpose y. And so we have our x and y values, and so all we need to do is program this equation directly, and then we can solve for beta naught and beta 1. So then what we do is we go back to this model, like once we've calculated what beta naught and beta 1 are, and we can multiply those by other x values, and we can calculate predicted values for y. And in this video, I'm not planning on doing like a training and test data set because I just want to focus on how we're solving the normal equation. The first thing we need to do, like if I go back to this model real quick, currently we have a vector of x's. Like that's what we have. And what we need to do is we need to add a column of 1s to our x vector and basically create a matrix that has a column of 1s and then a column of our x values. So the way that we're going to do that is I'm going to use the C underscore from the NumPy library, so it's C underscore, and I'll show you how to do this in the code. But basically what this does is it concatenates, or it joins matrices by rows, and it concatenates along the second axis. And I wanted to specify this here because it can be a little bit confusing about what's meant by the first and second axis in NumPy. So this axis is called, this is the 0 axis, but it's called the first. And then this axis is axis 1, but then it's called the second. So it can be kind of confusing. So with this np.c underscore, we're concatenating along the second axis, so that's this one. And so basically we're combining our combining columns to form our matrix. So let's go back to here. I need to add that column of 1s to x, so I'm going to call this xb, and this is equal to numpy.c underscore. So then what I need to do is I need to specify the two vectors that I'm combining. So the first vector is going to be a vector of 1s, and it needs to be a length of 50. So np.1, and then this is 50 and 1, and then we're concatenating this to x. So let's just see what this looks like. Alright, so you can see that we have our original vector of x here, and then we have a vector of 1s. And so this looks good, because this is the form that we need this in order to solve the normal equation. So now we can put in the code to solve the normal equation directly. So I'm going to say beta, actually I'll just specify, so normal equation, beta is equal to, so we need to take the inverse of the x transpose x, and so I'm going to use the inverse from the linear algebra module that's in NumPy, so numpy.linalg.inverse, and then I have x, b, and take the transpose of that, and then dot x, b, and then dot x, b, and then we take the transpose of that, and then this is dot y. So we should have some values for beta from this. It says there's an error. Oh, I need dot here. All right. So we get back 2.4 and 3. And if we go back and look at the equation that we used to generate this data, we used 2 plus 3x, and then we added noise to that. So if we had exact parameters, we would have gotten back 2 and 3. But it's impossible to get back the exact parameters from the original function because of the noise that we added. So we actually got back we round up, so 2.5 and then 3.1. What we can do now is use these beta values and put them back into our model to make some predict some values of y. So what I want to do is generate a couple values for x, and then we can use those in our model to predict some y values. Predict values for y. So let's say x predict is equal to np, and I'm just going to create an array. And this needs to be a multi-dimensional array because we're going to need to do the same thing that we did before, which is add a column of ones to matrix. So 0, I'm just going to say 0 and 3, and then just to show you what this looks like, so we have a multi-dimensional array. We need to concatenate vector of 1s to the first column. So x predict b is equal to, I'm just going to do the same thing I did before, so np.c underscore, and then we need a vector of 1s that has 2 rows and 1 column, and then this is this, and then we're going to concatenate that to our x predicted, or to our x predict. So let's look at what this looks like and add the b. All right, so we have our matrix. So now we can multiply this by our beta vector, and we can predict some y values. So y predict is equal to x predict b, and then we're going to take the dot product of beta. All right, so we should have some predicted values. So what I'm going to do is plot our original data, so the data that we generated with with our predicted data, and just see what everything looks like. So plt.plot, and then I have x, y, and I want to plot this as points, and then plot our predicted data, so x predict, y predict, and I just want this to be a line, and then I'll add some labels, so plt.x label x, plt.y label y. So then the blue dots are the data that we generated and used for our model, and then the red line is our predicted values that we got from that model. If you found this video helpful, please hit like or subscribe, and thank you for watching.